Okay, so in this video, we are going to understand the relationship between Ka and Kb. What is Ka? Both are equilibrium constant. We write the subscript A and B if A is going to be, if the reaction is going to be a dissociation of an acid, the equilibrium constant, which is also the ionization constant, which is also the dissociation constant, all are same. For acid, we write it as Ka. If there is a base and it undergoes dissociation, the equilibrium constant or the ionization constant or the dissociation constant for a base is going to be Kb. Okay. Now, I don't personally feel that this derivation is so important. All you need to remember is this. Okay. So, Kw will be K into Kb. Okay, so and this is what we are going to use in majority of the numericals as well. So the product of a dissociation constant of an acid and the dissociation constant of the base will give you the ionic product of water, and this you know is 10 power minus 14. Okay, so this should be 10 power minus 14. Ionic product of water, I told you it is going to be a constant. Okay, or in other words, if we are talking about pK, you can also write in terms of pKa, but there you will have pKb, which will be pKw, and that will be 14. Okay, at 298 Kelvin. So these are some of the things, which is the entire summary of this video, which you might be using in some numericals. Product is going to be ionic product, and if what is pKa minus log of K, pKb minus log of Kb, concentration of Kb, or whatever the value of K. Correct? So if you have pKa plus pKb, if you add it, you should be getting pKw, which is 14. Right? So these are the two things. Now I will do the derivation. Okay, but if you do not have time, maybe only this much if you remember also, it should be okay. But these are some things which are very, very important. Alright, so now let us understand, if I have an conjugate acid base pair, let us say ammonium ion and ammonia are conjugate acid base pair. How do we say that? I told you this, whenever we try to figure out if the given two substances are acid base pair, conjugate acid base pair, you have to understand that there should be a difference of a proton. Look at that, NH3, there is one proton extra here. So that means this is able to donate proton and you are getting this, or this, if it accepts protons, you are getting this. So clearly this is an acid, and this will be its conjugate base, or if you consider this to be the base, this will be acid. Right? So acid, this is the conjugate base. I will donate a proton to this will be the base. So from an acid, if after it shows acidic character, I am getting a conjugate base. If you consider this to be the base, it accepts a proton and this becomes conjugate acid. So if this is the base, this will be the conjugate acid. Now let us take an example here. So in both the cases, what happens in aqueous solutions? So if you say you have water, what happens this in the aqueous solutions, what happens? Okay, now this is an acid, so it donates a proton and gets converted into its conjugate base, and this is my acid, this acts like a base, right? So here it will be H3O plus, it accepts a proton and you're getting H3O plus aqueous. Alright, so similarly, if I have, let me write this is an acid reaction. So what will be the value of Ka here? Concentration of hydronium ions into concentration of ammonia divided by concentration of ammonium ions. We do not write water because it's a liquid. Now if you take the same reaction for ammonia, for example, ammonia plus water in aqueous, right? So this is my base, water acts like an acid, and what happens here? Ammonia, when it accepts a proton, gets converted into ammonium ion. So this is its conjugate acid, and this loses, so it is my conjugate base. And what will be the Kb for this? Kb for this will be concentration of the products, okay, OH and ammonium, and divided by concentration of the reactants, which is ammonia here. Alright, now let us say this is my equation 1 and equation 2. In case I add 1 and 2, what happens? Let us see. I get something called as a net reaction. If I add 2 or 3 reaction, the resultant is my net reaction. Let us see what is happening. Look at that. Okay, so you have ammonium here. Okay, so this part is going to cancel out. Ammonia here in the reactant, here in the product. Okay, so what do you get ultimately is 2H2O is giving you ammonium ion plus OH negative. And what is this? This is nothing but, you remember, two molecules of water, H2O plus H2O, one acting like a base, one acting like a acid. Okay, and what is this ultimately giving you? This ultimately is giving you the ionic product of water. Right, if I write the concentration of this, you do not consider, you are going to get 10 power minus 14, sorry, yes. And at STP, if you calculate this, you are going to get this as on experimental, Ka is going to be 5.6 into 10 power minus 10 and Kb was 1.8 into 10 power minus 5, excuse me, yes, okay. So this was this much and this was this much. Now, if you multiply these two, just for the sake of multiplying, I could see that when I do, okay, let me write it here. Suppose I multiply Ka and Kb, that is 5.6 into 10 power minus 10 into 1.8 into 10 power minus 5. I was getting 10 power minus 14. So that is how I concluded that, this is going to be the equilibrium. I mean, the product of Ka and Kb is going to be Kw. Okay? Yes. Now, most important thing here is, this is a net reaction, like I said, you need to remember. Also, there is one more way to figure out. I can even multiply this and see that some things are getting cancelled, and that is how I am getting the ionic product. I have written it in the book, you can just check out. Okay. Another way of arriving at this is analyzing only a base reaction and then concluding it, which is also written. Okay. So, anyways, if they ask you the proof, you can do it this way also, or you can multiply these two and do. All the three ways are there in the book. You can just go through it. This is also fine. Multiplication, I'll just show you. So this is the multiplication and you're verifying. This is what I have done now. This is what is there. And this is the third way. Okay, you start from a base and finally you see you're arriving at the same result. Okay, so how do I write it in a general form? Alright, so let us now understand how to write it in a general form now. The general form is, if you have a net reaction, the equilibrium constant for that net reaction can be obtained after adding two reactions. Net reaction is like adding two reactions. You add two reactions and you're getting net reaction, and for that net reaction the equilibrium constant will be the product of the equilibrium constant of the individual reactions. I have written this statement. So if you have reaction 1, reaction 2, reaction 3 for example, if you figure out that if you add this you are getting some one reaction which is called the net reaction. Okay, if you have a couple of reactions and if you are observing that an adding you are getting a net reaction, the equilibrium constant of this reaction, which I call it as K net, will be equal to K1 into K2 into K3. So if I observe that I have a couple of reactions, when I add that I am getting some net reaction, the equilibrium constant of that net reaction is the product of the equilibrium constants of the individual reaction. This is all you need to ultimately remember. Okay, now if we are telling it for a conjugate acid-base pair, this is valid for a conjugate acid-base pair. This is specific. If I write Kw, it is specific. This is the general equation. This is the general. Okay. When can I write Ka into Kb is equal to Kw? This reaction is specific for a acid-base conjugate pair. Okay, so if I have an acid and a base which is the conjugate pair of that acid, only then. I cannot just write it for any any acid and any base. Like I cannot write it for HCl and some random base. Okay, so I should have an acid base conjugate pair. And how do you identify? I told you the difference should be one proton. Let us say I write HCl. Okay, then I can write it for Cl negative, because this is an acid, it loses proton. Okay, and that when it loses proton, it becomes Cl negative. Okay, and let us say this is my acid, correct, and this is my base in that case. So for this conjugate base, I can write this reaction. I cannot do it for in general anything. Okay, so I repeat, or if I have a base, let us say I have NaOH, this is my base. So base, when it accepts proton, now here we do not, this is not relevant for Bronsted-Lowry's base. I mean, this is a Bronsted-Lowry's concept, so maybe for ammonia, I think we already discussed. Okay, maybe for OH negative. If this is my base, correct, it accepts a proton and get converted into water. This is my conjugate acid. So if I have a conjugate acid base pair, then it becomes valid. Okay, now quickly I do one numerical, and this concept should be clear to you. Again, this is a worked example of your textbook. Whatever I've written on the top, product and pKa plus pKb equal to 10, 14, that you need to remember. Okay, now let us do this. Determine the degree of ionization. So this is worked example 7.23. Okay, determine the degree of ionization. Determine the degree of ionization and pH. Okay, you have to also find the pH of a 0.05 molar ammonia solution, 0.05 molar. Ionization constant of ammonia is given to you. Okay, ionization constant for this is given to you as 1.77 into 10 power minus 5. Calculate the ionization constant of conjugate acid. You have to find the ionization constant of conjugate acid of ammonia. So you have to find alpha, pH and these three things. So let us write the reaction. What is happening? Ammonia is given to you. You know it is a base, right? So what happens in an aqueous solution? It is a base here. It accepts a proton and this will be its conjugate acid, and then if it accepts a proton, this gets converted into OH minus ions. So what is it that you need to find? Alpha, pH of this entire reaction and the ionization constant of ammonium ion, which is its conjugate acid. You have to find this part is basically ionization constant of ammonium ion. Let us start this. You remember whenever you are supposed to find the degree or the extent of ionization, you have to write the table. So let us say this is my initial concentration. I am started with 0.05 molar of ammonia. Initial concentration is this much. So let us now write the dissociation extent. It is minus 0.5 alpha. I remember I told you alpha is the extent of how much of ions are getting converted into these, how much of ammonia is getting converted into ions for 1 mole. So now we have 0.5 moles, so it is 0.5 moles into alpha, and here also it is 0.5 moles into alpha, 0.05 moles of alpha. So at equilibrium, what will be the concentration? 0.05 minus 0.05 alpha. This is 0.05 alpha. This is 0.05 alpha. And remember, this is a base. So what it will be? Kb it will be. So Kb will be concentration of the product. So I'll write it directly. 0.05 into 0.05 alpha square by concentration of the reactant. I will take 0.5 common, 1 minus alpha. So you can see that this is getting cancelled. Now alpha is very small, alright, so I can ignore this, otherwise you'll end up having a quadratic and all that. So just to simplify it, I will ignore it. Okay, you can find it out also, but this is the way it's done in your book, so you can ignore because it's very small. So this denominator will be 1. So what do I get? Kb is 0.05 alpha square, and I know the value of Kb here. It is given to me. So this is 1.77 into 10 power minus 5. If you calculate alpha, you get alpha square first. Take the square root, you will get alpha. Alpha will be equal to 0.018. So the first part is done. 0.018. Okay. Now I need to get pH here. So to get pH, I need to know the concentration of H plus. There is no H plus in the equation, but I have OH minus. So first let us find the concentration of OH minus. Okay, so the concentration of OH minus will be 0.05 into alpha, which is this part. Okay, so from the reaction I get to know that at equilibrium I am having 0.05 alpha moles of hydroxyl ions. So that's why I'm just substituting here. And what do I get here is 9.4 into 10 power minus 4 molar. Okay, this is what I get. So what will be the concentration of H plus? You know at equilibrium it is going to be 10 power minus 14, the ionic product. So this will be nothing but ionic product, which is 10 power minus 14 divided by concentration of hydroxyl. Okay, because how did I get this? The product of H plus into OH should be equal to 10 power minus 14. So now I will get the concentration of H plus, which is 1.6 into 10 power minus 11. So once I know, or you can also do POH directly, and from 14 you can subtract, that is also fine. Or you will do this. So what will be pH now? Minus log of H plus ions. So it is minus log of this much. I told you how do you calculate this. So this is going to be 10.97. Okay, so this is going to be 10.97. Yes. Okay, now what is remaining? This is done, this is done. You have to find the ionization constant of ammonia, which is its conjugate acid. Okay, now separately you don't, either you reverse it and then do it, which we don't want, right? So the easiest way would be to, ionization constant, right? So Kw is Ka into Kb. So what will be Ka? Kw by Kb, just now whatever we have done. So it is 10 power minus 14 by 1.77 into 10 power minus 5. This comes out to be 5.64 into 10 power minus 10. This we could have done independently, but all these calculations was done to figure out H plus and alpha. Yes? Okay. The next video I will be covering di and basic acids, polyacidic bases, factors affecting the strength, and common ion effect.